Okay, and here's the example that we're going to do. We are going to, I don't know what the instructions are for this. Can you guys hand me the page? Yeah, the book page. I wanted to do this before you guys had to do 16 and 17. So it says, find an equation of the tangent line at each point on the given, at each given point on the curve. So I just wanted you guys to have an additional example of that because the problems can get kind of funky when you do them. And I wanted you guys to be able to see them. So let's go ahead. We're actually, you guys end up having, I don't remember which ones you get assigned. But it looks like I wanted to do number 18 with you, so I do not think I assigned that one. I must have assigned 16. Is 16 assigned to you guys? Yes? Okay. So we're going to go ahead and we're going to do number 18. So we're going to do the parametric equation, x equals t to the fourth plus 2, y equals t to the third plus t, and then the tangent lines that we're going to be writing, find an equation of the tangent line at each given point. We're going to have the points 2, 0, 3, negative 2, and 18, 10. And there was one of these on the worksheet, but I just wanted to kind of walk through it just to give you guys an extra example. I didn't even do all three of these. Okay. All right, so what do we need to do to find a tangent line at a given point? We need to find the derivatives. Okay, so we need to know what dx dt is, what dy dt is, so that we can find dy dx. So do you guys like calling it dx dt, or do you guys like calling it x prime? X prime, okay. So I'll say x prime of t, and what would that be? Or t to the third, okay? And then y prime is t squared plus 1, okay? So now we have that, and then from that, what do we need to do? dy over dx, and what do we get? Okay, so now we've got that. Okay, so we're going to find all three tangent lines. So the first tangent line we have, we're going to do for 2, 0. So what should we do? Yeah, we have to solve for t because our derivative is in terms of t and our point is in terms of x and y. So we can't just like take the point, plug it into the derivative like we're used to doing in regular problems. Okay, so the part you have to be careful of is you can't, sometimes it'll work in a problem to just take the x value and set it equal to the, just take the x parametric equation and set it equal to the x value, or just take the y parametric equation and set it equal to the y value. But sometimes there will be more than one solution, and if you only use one parametric equation, you might be using the wrong one. So really what you should do, just to be careful, is use both, just in case, just to verify that you're using the correct one, okay? The safest bet is if you can see that the parametric equation is the type of equation to only have one solution. So if you look at the worksheet, what number was it on the worksheet where you had to do this? We just did it on the worksheet. It was like the second to the last one or something. Yeah, on 6, one of them was a linear equation you were solving, the other one was a quadratic equation. The linear equation is safer because a linear equation only has one solution. The quadratic equation not as safe because a quadratic equation has two solutions. So the quadratic equation, one of them could have been the extraneous solution, one of them is the actual solution you should be using. Does that make sense? So when you're picking these, you would want to pick it with just kind of being careful. Now here, we have one of them is t to the fourth, one of them is t to the third, so both of them have potentially more than one solution, which means in this case we're going to have to like use both of them to see which one has a t value in common. Does that make sense? So you just want to be careful as you do it that they agree on a t value, and sometimes you have to use both of them, not just one or the other. So that's something that students don't always watch out for, and then they end up using the wrong t value, and that could be something that could make you get the problem wrong. Okay, so what I'm going to do is I'm going to take this and I'm just going to say t to the fourth plus 2 equals 2, and I'm going to say t to the third plus t equals 0. And I just want to make sure that I get the same solution for both of these, just that they match up. So if I look at this one first, how would I go about solving that? Okay. T to the fourth equals 0, and then what would I do? Fourth root it, yep. Fourth root the other side, and the fourth root of 0 is 0, okay? And then if I was to solve this one, how would I do that? Starts with an F. Factor out a t, right? We have a GCF of t. That would leave us with t squared plus 1. And then you might be a little rusty on this. T squared plus 1. Anyone remember what type of solutions that would give you? It would give you positive and negative, but what type of solutions would they be? They'd be imaginary. T squared minus 1 is difference of squares, and that would give you plus and minus 1. This would give you plus and minus 1i. These are imaginary solutions. So this technically gives you nothing. So what solution do we get for the GCF outside that we took? We get 0. So we got the same solution for both of those. So we're going to use a t value of 0. So we have the point, we have the x and the y coordinate, and then we have a t value of 0. So now what do we need to do? Yeah, dy dx evaluated at t equals 0. So we have 3 times 0 squared plus 1 over 4 times 0 to the third. And what slope do we get? Infinity, aka does not exist, or undefined, okay? What types of lines have undefined slopes? Vertical lines have undefined slopes. And how do we write the equation for a vertical line? X equals a number. Okay, so go back to your point. If you have to write the equation of a line and it's x equals a number, what would that number be? X equals 2. So the equation of our line is x equals 2. That was a weird one. Does that one make sense? It got a little funky in there. Okay, let's try the next one. So we have the point 3, negative 2. Okay, so I'm going to say t to the fourth plus 2 equals 3. t to the third plus t equals -2. I don't even think I can solve that. So we're just going to see, what this answer is, and then if we get more than one, then we're going to see which one fits in the other equation, okay? That's all we'll do. So how do I solve the first equation? Okay, subtract the 2. Okay, and when you 4 through, what do you get? Plus or minus 1. Okay, and so now we need to go to the other equation and we need to see which answer makes sense. Is it just +1 or is it -1 as well? Okay, so if I plug in +1 to the third plus +1 equals -2. No, okay, so we're going to say, I'm going to write these both down. T equals +1, t equals -1. +1 did not make sense. Okay, t equals -1. -1 to the third plus -1 equals -2. That one makes sense, so that's the one we're going to use. Okay, so dy dx evaluated at t equals -1. So we've got 3 times -1 squared plus 1 over 4 times -1 to the third. So 4 over -4. So what should we write for our tangent line? Perfect. Okay. And then let's go ahead and do the last one. So we've got 1810. So t to the fourth plus 2 equals 18. T to the third plus t equals 10. Okay. So what do I do? Subtract the 2. T to the fourth equals 16. Gonna fourth root it. What's the fourth root of 16? Not just 2. Plus or minus 2. Okay, so positive 2 to the third plus 2 equals 10. Yes, okay. Negative 2 to the third plus -2 equal, okay, so -2 is not going to work. Okay, so we're going to use 2. Now we've got dy dx at t equals 2. 3 times 2 squared plus 1. And what are you guys getting? I multiplied it wrong. Oh, that's right. There we go. There we go. Okay, 13:30 seconds. And this is our equation. Okay. Beautiful. Okay, So we see how important it is to use that second equation. We truly cannot, and it saves us time because we wouldn't want to have to do like 2 tangent lines for each of these when in reality one of them is probably the answer and the other one's not. Okay, so just keep that in mind when you get to the tangent line problems, especially, so I used to do problem 15 as an example, but it is kind of brutal. And so I chose not to do that one this time. But so do your best on 16 if you want us to go over it in class a little bit, we can. It's just that the sine and cos are much nicer than cotangent and sine squared, as you can imagine. So, alrighty.